Good morning and welcome again to the third in the series on the slowing speed of light, which has shown so far that the universe is not expanding. Therefore, the Big Bang theory is debunked, finished. And it also casts great doubt on relativity, because relativity was needed to explain why light from fleeing galaxies could always come back to us at the speed of light, even though those galaxies were speeding away. So relativity has become irrelevant. And we had to have relativity before we had the Big Bang theory. The one had to have the other. So they both depended on each other. If one's gone, really the other one's gone too. And we'll leave it there. Josh has asked this morning about the speed of light. What's the speed of light this year and how can we be sure? So we're going to have a look at that briefly this morning. But our main thing we're going to do this morning is dismiss deep time dating by radioactive measurements, so that all your billions of years are reduced to thousands. I'm going to show why, and we're going to study it now. So I hope we do okay. I'll be referring from time to time to the little pamphlet, Deep Time Dating Dismissed, which is on the website LOLO, that's LOLLO, that's Lima Oscar, Lima Oscar.org.nz. So if you might want to look at that. There's a few papers up there. Okay. I don't need those at the moment. We'll have a look this morning at the speed of light, and I'm going to need my pens, and I'm not sure where I left them. I'll just have to excuse myself a minute. I'm back. Did you miss me? I'm back. And here, up the top here, we have the speed of light for this year. So I'm just going to write it nice and big so you can see it. It's 297,935.263 kilometers per second. Now you should be able to see that. Now it's decreasing this year by just under 24 kilometers per second. And I haven't got that result there, but here's last year's result for this is 2022, by the way, here. 2022, the year 222. And in 2021, the speed decreased by 23.876 kilometers per second. That's per second, seconds to the minus one, kilometers per second in 2021. If you want to know the result for this year, you take this year's and next year's, if you like, or last year's and this year's, and you can see how much it's decreasing by. I take last year's speed of light and this one, and subtract the one from the other, and you've got it. It's not hard. So I'm going to show you how to do that, because Josh has asked this morning, how do we get the speed of light? How can we be confident? Right now, I'll just write up here at the moment. As you all know, the standardized speed of light is 299,792 point something, and I've seen it to 20 decimal places at the university, just visiting, and they're very sure of it, but it's a bit different from this one, isn't it? 299 is a bit different from 297, and so there's quite a decrease, and we can show that this speed here was the speed in 1945. All right, That was the speed in 1945. Now, I showed you yesterday on the board that the symbol for wavelength of light was lambda, and the symbol for radio decay rates is lambda. And that the two are the same. They're the same thing. The decay of light and radio decay are exactly the same, because as the speed's decaying, the wavelength is getting shorter, and at the moment it's getting shorter by 0.0024 of a wavelength. That's not very big, I'm sorry, every 3 years. And that's important to just keep that in mind, that the wavelength's getting shorter by 0.0024 of a wavelength every 3 years, and that's the decay of light. Don't get this 24 here mixed up with this 24 kilometers per second. They're not the same. That's just a different way of looking at things. It's just, that is coincidental. This is not, if I may say. Now, I can rub that out now, and I'm going to rub that out, and we're going to have a look at how to obtain the speed of light for any year. There we are. I'll have it for you in black and white this morning. I'll put my blue pens down for a minute. I'll have it in black and white. And now, Barry Setterfield and Trevor Norman, a couple of speed of light researchers, they, years in the 70s, took all the known determinations of the speed of light. They were about 100, and they made a graph, if you will, and they plotted these speeds on a graph. Whatever they were, they plotted them on a graph, and they decided that the best fit for that graph, they did at Adelaide University, was this. That was the best fit of the graph. Now, that's the speed here. That's the speed of light down there. And this is the date going back. That's the time, if you like, time. That's the date going back. Now, that was all very good, and they determined, of course, since they had a time down here, they could determine a date here at which the thing just went off the charts, and it's asymptotal, never touches this line, just touches it somewhere up around the moon. Okay, just touches it. The speed of light was amazingly fast, and then just plummeted, and it's just trickling along today in terms of what it was before. So that's the graph they got from some sort of weighted statistical method of doing all this stuff. I don't really quite know what that's about, but that's what they did. Barry Setterfield, Trevor Norman, in the 70s, Adelaide University. Now, he got a date. I better tell you about that. He said it was something over 6,000 years ago. 6,000 plus years ago. And that this happened here. So, a couple of things that drove the Lotto research was this. The first that was done was refining this date, just getting it spot on as we thought, and this was placed at 4219 BC. That was placed there by Mrs. H. You'll find her on the website. 4219 BC. And We also, why it's called LOLO, L-O-L-L-O, it stands for limit of last light out. And the reasoning was this, that if we have a distant star, I'm going to draw it here, have a distant star here, what was the maximum distance that star could travel since the speed of light started reducing, since it fell, if you will, since the fall, since that fall in the speed of light. How far, to the astronomer's eye tonight, could that light have travelled in that time? So that was the question, and the answer that was posed was 1.5 billion light years. 1.5 billion light years. Now, yesterday we did a little bit of talk on 1.5s, and it's a number that keeps popping up all the time in this work. We talked about a distribution between 1.35 billion light years out, 1.35 billion light years out, a distribution of those little 0.00024 speed jumps, if they like to call them, of 72 kilometers per second, but it's incremental decreases in the speed of light as it's coming in. And at this point, the so-called, what they used to call recession speed, at this point here, was 900 times 72 kilometers per second. This is what was observed by redshift measurements, and we have 900 divisions of 1.5 of 72 kilometers per second between here and here. Now, if we've got 900 divisions over 1.35 billion light years, each one is 1.5 million. 1.5 million light years per, now I abbreviated 0.0024 to 2.41. There we are, that was the original finding, 2.41 per 2.41. So it's 1.5 per 2.41. And this, you note this 1.5 billion light years here, I'll tell you how we determine that later, but this 1.5 billion light years here, if you look at it, a 1.5 upon this is 10 upon 9. Does that make sense? If you look, compare the 1.5 upon that is 10 upon 9. So this at this point here, this 1.5 there is 10 ninths of this. 10 ninths of this. So this 10 ninths, there's your 1.5, and there's your 1 upon 2.41. And those are the numbers that I said were closely connected with radio decay. And the other one I said was 6224. Because at 2006, when this thing was first discovered, there was 6224 years elapsed since this date here. Okay, so we'll have a look at that in just a minute. So 6224 years elapsed. Now, as long as you've got the idea of this graph, And keep an eye on that graph. And I'm going to tell you at the moment that when you measure things in light years, your time and your distance are really the same on the same line, because the two are intertwined. If you measure in light years, your time and your distance become intertwined. So this graph, whether you have a time axis down here or a distance axis, it doesn't matter. Okay, so we're just going to, I think I might just rub most of that out, and you got all that? There we are. Out she goes. We'll keep a little bit of that. Keep a little bit of that. Now, I'll just rub it out. Josh wants to know how we determine light speed before we go any further, and we'll just do that now. So I've given you some groundwork there for deep time dating dismissed, but we'll just break into, for those who are interested, the rest of you make a cup of tea, how to determine the speed of light at any year. Now in 1880, George Forbes made a determination of the speed of light. And his determination is in print, not on the internet. 301,382 kilometres per second. And if I got that wrong, it's on the website correctly. Now, if we've got a date and we've got a speed, we can work from there, and I'll show you how this works. So we'll draw another graph. Now, if we've got something that's slowing down, right, and this is time, and this is speed, distance achieved, this is distance, and the times are even all the way through. If it's slowing down, in the first part of its thing, it'll gain a lot of distance, right? And then in the next part, it'll gain a bit less distance, see? And in the next part, it'll gain a bit less distance again. And in the next part, it'll gain a bit less distance again. And so we've got a curve that goes like that. Is that okay? Is that firm enough for you? And this is actually a mathematical function. Now, mathematics, it talks about real life. And this is the function of y equals the square root of x. That's the general function. Or if you like, distance equals the square root of time. Now, if you want to find out the slope of that curve at any point, that gives you the speed at any time of a slowing, the general function for slowing speed. If you find out the slope of it, now mathematicians are very clever, and they know this equals x to the power 1/2. And what they do is if they want to find the speed at any time, they say, right, well, we go, it must be 1/2. And they take 1 off this, so it's x to the minus 1/2, so it's 1/2, or 1/2, the square root of x. I didn't do that very well, did I? But that's what it is. 1/2 the square root of x is the speed. And we're not going to go into any mathematics, I'll get myself into trouble. The speed is that. For that slowing down function, that general slowing down function, the speed is that. So if x here is the time and y is the distance, and we want to find the speed, that's the distance per second, isn't it? And so we can find the speed of light by doing this. If we take that the speed equals 1 upon twice the square root of the elapsed time of the time elapsed since the speed of light began to fall away. And we know that because it began to fall away in 4219 BC. I'm trusting Mrs. H on that. You can write a letter if you don't like it. And all we've got to do, then we've got a speed here. So it's 301,382. But George Forbes actually did it in meters per second. But we'll just leave that there for now. And all we've got to do is put the elapsed time at 1880, right? So we've got to do a sum here. So we go 4219 BC plus 1880. And because we've gone through the BC AD barrier, we've got to take off 1. Trust me, everybody knows it. You take off 1. So we're going to make that an 8. So that becomes 8, 9, 10, 6. 6,098. I hope I'm right. It's a bit early in the morning for maths, but we'll put a 609 there. So oh 98, and the same here, and that's supposed to equal this number here, but we've got years here, and we've got meters per second, so we've got to actually have a constant to rectify that problem. So what the old maths before metrics, we always used to have a constant up the top here, like that, a certain constant, and up the top, just to adjust between meters per second and years. You always had a constant. So it's 301,382. 382 equals this. Now, it's very easy to find the constant now. We can find the constant because we've got a speed, we've got a year. I haven't put the comma in here. We've got a speed, we've got a year, and we can find that constant. So the constant equals 301,382 times twice the square root of 6098. And this result was actually in meters per second, so it's actually that. And the result of it anyway is that this result here is 4707 times 10 to the 7. That's your constant. So if you want to know the speed of light for any year, you can just pop in that 4707 times 10 to the 7th, and you have the speed of light for any year. And it works. Now, I don't think it's a coincidence that for 1945, if you put the 1945 date here, you'll get 299,972. Or if you put the 299,792 here, sorry, you'll get 1945 down here as a result. And it's no coincidence because the atomic age began in 1945. And atomic clocks have been used to hold the speed of light constant ever since. The atomic clocks are slowing down at exactly the same rate as the speed of light slowing down. And today they measure light speed by a laser beam and an atomic clock. So that as the light slows down, the atomic clock slows down and the speed of light remains the same. And the same sort of thinking, I think, that gave us the same symbol for wavelength and the same symbol for radio decay, the same sort of thinking has the speed of light fixed at 1945. We'll say it's just a memory aid for them to remember how it's all done. And it's not something that's pushed today. I'd say it's been swept a little bit under the carpet to make way for the continuance of the Big Bang Theory. So we'll just leave it there. I think that's enough. Josh, has that explained it? Josh seems to think that's okay. So we'll talk now about deep time dating dismissed. I'll just rub this out. And remember old George Forbes? He published his result to 6 decimal places in 1880. It was an improvement on Armand Fizeau's method of determining light speed. And improvements always lead to a more accurate sort of a determination, don't they? Very good. Good on you, George. And we'll just rub that out. Now, long before that 1.5 averaging was found in the speed jumps, if you like, the 72 kilometre speed jumps which exist between the astronomer's eye tonight and 1.35 billion light years out. The 1.5 popped up in the decay of uranium and the zircon crystals and granite. Can they see me up there? They can probably see me up there. There's a bit of granite up there anyway on the shelf. It's the stuff they make kitchen bench tops out of. It's beautiful stuff. And it's also the basement rock of the earth. That's what's down the bottom. If you hit basalt when you're drilling for oil, give up, mate, because it's not there. It's only in the sedimentary layers above, the water laid down layers above. So anyway, I've got to get back to it. 1.5 billion years. Here's an actual photographic picture of the zircon crystal in granite. That's really what it looks like. It's absolutely true, and that's it there. That's it. That's the zircon crystal in granite. And inside the zircon crystal, there's uranium, uranium-238. And of course, uranium ticks away, and uranium has produced lead. So in there's lead. That's in your kitchen bench top. In there's lead, and in there also there's helium, because helium is a byproduct of uranium decay. So in there is helium. Now, scientists know how much lead is in there, and they know how much uranium is in there, and they say, well, that uranium is exactly 1.5 billion decay years worth of decay in that uranium. They say it's 1.5 billion decay years, that's 1.5 billion years old. But we know, of course, that the speed of light being faster, the rate of radio decay has been faster, and that 1.5 billion years hasn't been that long. In fact, it can only have started when radio decay started, when the speed of light fell, because the two are the same. And if you had very fast speed of light and radioactive materials, all the radioactive materials would have just gone sizzle fits and gone. But today we have radioactive materials, and the two started at the same time. The initial rate of radioactivity was tremendous, but brief, fortunately. And so the two started at the same time. But anyway, getting back to this, here's 1.5 billion decay years worth of decay in this closed system of the zircon crystal. And it was reasoned that if the work done by radio decay was 1.5 billion decay years worth of decay, then the work done by a travelling particle of light, if you like, a photon of light, during the same period since CDK started, speed of light decay, must be 1.5 billion light years worth of distance. So that's where the 1.5 billion light years came from. That's in paper CDK1 on the website. That's where it came from. Now, what I'm getting to here, slowly, is that you've got your 1.5 billion worth of decay years there, but also in this thing here, you've got helium leakage. You've got helium leakage because your helium is quite a slippery gas apparently, and even though this is a closed system, there's helium leaking out all over the place. It's leaking out, and they can detect that helium, and they can detect how fast it's leaking out, and they can also measure exactly how much helium is in here, and they weigh the two up, and they say that helium's been leaking out for 6,000 years. So which is the clock that tells you when radio decay and speed of light decay began? Is it this one? Was it floating around the universe somewhere and jumped into the crystal then started decaying? Or was it this one here when it was in the crystal and it was not radioactive, and then speed of light decay began, radio decay began, and it began decaying inside the crystal? That's what's happening. So we've got the 6,000 years here of helium decay. Now, science, they write it, I'm going to be fair to them, they write 4,000 plus or minus 2,000 as one result. One result I've seen. Sometimes they say this, but often you get this. But we all know it's this, really, don't we? We all know it's that. So this here is where the LOLO idea comes from, the limit of last light out, 1.5 billion light years to match the decay years in this crystal here. Now, I'll just might refer to my notes here and just see if I've missed out on anything here. We've got a start to radio decay. The original speed of light was very, very fast. If radio decay had existed then, all the radioactive material would have decayed away in a flash. Very fast light speed, very fast radio decay. But we still have radioactive material today. This means that radioactive decay only began when light itself began to decay. Slowing light means decaying light. Now, we've talked about helium. We're going now to talk about polonium radiohalos, right? Now, I want to show you further that radioactivity had a beginning. And we're going to rub this out. Can I rub this out? Or it might work over here. Tick away quietly over here. Now, the black stuff in granite, it's called biotite, and in that biotite there are tiny specks of radioactive material, well they were, they've decayed away most of them, that have left rings like that. When they slice the biotite very thinly, and when you take a sphere and you slice it through and you turn it up so that you can see that there like an orange, you get these little rings showing in there, and these are pleochroic radiohalos, they used to call them, but they are little rings in the granite, and some of them are from uranium. They have all sorts of different rings around them where different decay products have stopped. So the uranium decays, the different alpha particles or beta particles, whatever they are, come out and they stop, bang, and because they only go a certain distance, each one, they've got a certain power, where they stop, they leave a mark. Now, some of these pleochroic radioheroes, and his name's Robert Gentry and his son, they have studied these radio halos, they call them, these radio halos, and sometimes there's only a couple of rings like this, and they know that the stuff in here is polonium, not uranium-238, but polonium. Now, polonium is only known as a byproduct of the decay of uranium down to lead. It never exists on its own. It's got a very, very brief half-life even today at today's slow speed of light. Nanoseconds in some cases. There's about 3 varieties of polonium, but there's these polonium specks in the hard granite, right? And they know it had to be hard to leave a mark, so it had to be hard when it left a mark, and there's a very, very brief radio decay time. Now, Robert Gentry, he's got his own opinion on it, but I believe that this polonium, primordial polonium he calls it, was in the granite and then became radioactive. It was hard, the granite was hard. There's no reason to think granite has ever been molten, by the way. It was hard, and these things became radioactive and bang, left their mark like that. And they're all over the stuff. And it shows really that there had to be a beginning to radio decay after the granite was formed. There had to be a beginning to radio decay. So this points again, you've got your 6,000 years here of helium, on the helium clock. You've got your beginning, again shown in the granite here, your beginning to things, so that granite, in fact, is quite a fabulous rock. Your bench top tells a bigger story than the university will tell you. So now we're going to talk now about how deep time dating is dismissed. And I'm going to rub this out and we'll talk about how fast the speed of light's been in the past. I've laid the groundwork for it, and you should be okay with this. You should be okay with this. Now, it's not that I want to knock science. Science is a wonderful thing, but the stories that are produced aren't that flash. And it's not that I'm here to knock the science. Robert Gentry and Bill Tift and all these other, Fred Hoyle and all these other astronomers, they've done a wonderful work over the years. But I think it's all been pushed aside by the Big Bang story in a way. So anyway, we'll remember our graph. Here we go. Now, the graph of the falling speed of light is exactly the same as our graph we drew before. This can be time, if you like, time. That can be the speed. There we are. And or this can be the distance. Either or, time or distance. We'll make it distance this time. Light years are a slippery thing. They're mixing a speed and a time with a distance and a time together. So that's your distance, and remember, as we look out to 1.35 billion light years out, as we look out to there, remember that there are 1.5 million light years of light travel per 2.41 change in the wavelength of light, or so there are 1.5 million light years of travel. Now we did the zones of thousands yesterday. Remember, at the local zone, at the astronomer's eye, right here, we have got a local zone of units, because today we've said earlier that the speed of light is slowing by 24 kilometers per second per annum, all right, per year. And if we take 3 of those, 3 years, if we take 3 years, it will have slowed by 72 kilometers per second, which is a speed jump of 0.0024 of a wavelength of light. And remember, we abbreviated 0.0024 to 2.41. It's just handier, and it works well. That's from 2006. It's decreasing all the time. And if we look today, there are 3 light years of travel per 72 kilometers per second speed jump, we'll call it. That little jump, we'll call it a speed jump. And here, there are 1.5 million light years per speed jump of light travel. 1.5 million light years for each 2.41. There are 900 divisions of 72 kilometers per second. That's the increase between here and here. If you divide this by 900, you get 1.5 million light years average each speed jump. Now, what's the difference? And it's a tricky mathematical thing, between 1.5 million and 3. How much bigger is 1.5 million than 3? I'm going to give it to you. It's 500,000 times faster. 500,000 times faster. Or more distance, if you like. Now, if you had something which was coming in, the frequency didn't change, but the wavelength did, the frequency didn't change, that would be a speed. That's 500,000 times faster here, on average, than it is today. 3 light years per year, okay? 3 light years per 0.0024. And here it's 1.5 million light years per 2.4 here. So it's 500,000 times faster, but you've got to look at this area in here. This area in here, this is huge. It might be brief, but it's enormous. It just keeps going. And So we've got to say 500,000 times plus, all right? 500,000 times plus, at least 500,000 times faster. Does that make sense? Now, if the speed of light is 500,000 times faster, on average in the past, and had a beginning, how much faster in the past has been the speed of radioactive decay, on average? And the answer is 500,000 times faster at least. If light has been at least 500,000 times faster in the past, then radio decay must have been 500,000 times faster in the past too. All right? So that all radioactive dating has to be reduced by 500,000 times or more. And no radioactive dating can date back before 4219 BC. None. Because that's what the graph says. I didn't say it. Setterfield and Norman said it. That's what the graph says. That's what the statistical results got. It's all been dropped now. Nobody's following it. But that's what it says. Because they just don't. Anyway, we're going to have a look now at what it does to some dates. Can I rub that out? I'll rub it out. Here we go. I hope you got it. 500,000 times faster at least. The speed of light on average. So the average rate of radio decay has to have been 500,000 times faster at least in the past. We'll just have a look here. We'll just rub that away. And now, everybody knows the accepted age of the Earth from radio decay. Everybody knows that. The accepted age of the Earth from radio decay is 4.6 billion years. Now, I'll have to abbreviate that, there we go, billion years. 4.6 billion years. It's actually exactly the same as uranium decay, but they fiddle around, they get it another way to say they didn't get it that way, but it just works out the same anyway. So it's actually 4.6 billion years. That's the accepted age of the Earth. Now, when you reduce that by 500,000 times, at least, when you reduce that by 500,000 times, at least, now I'm not saying this is the age of the Earth, I'm just saying this is how they date it. You can have any age of the Earth you like, it's a free world. But I'm just saying this dating method doesn't work. And I'll show you why. Because this age here, any date you get, has to be reduced by 500,000 times at least. All right? 500,000 times at least. So when you reduce this by 500,000, I think if I'm lucky, what do you get, Josh? I get 9.2, is it? 9.2 thousand years. Now again, I'm not saying that's the age of the Earth, I'm just saying that's what the radio decay has to say, because it's been 500,000 times faster in the past. So if you measure at today's speed, you're going to be 500,000 times out, and you're dating. And at least, now I'm going to suggest, I'm just going to suggest that since light goes in threes, it's decaying by thirds. And if we have one wavelength plus a third of a wavelength plus a ninth of the wavelength plus a 27th of a wavelength, how much wavelength will we have? I'll show you. 1.5. And I reckon there's a decay process going in there of thirds to bring up 1.5. There's also a minus 1/2 series that will give you 1 upon 1.5 or per 1.5. There's also a series there if you start with 1 and keep adding these in. So it's funny that a half and a third pop up, and I'll show you that in a minute, but I'm going to say you can reduce that by a third and you come around to something like 6,000 plus years is what they're really getting for a date since radio decay began. That's all I'm saying. Since radio decay began, and that's pretty good, isn't it? Pretty good. So the at least, I would say, would be take another third off. Happy with that? And we're going to, I think that's sort of rounded it up. That's pretty much how deep time dating is dismissed. Every single radio decay date has to be reduced by 500,000 times at least. The billions, every billion reduces to thousands. And really, if science wants deep time dating, and they're welcome, another way's got to be found, because this way's not working. It won't work at all. Now, just as an afterthought, if you've got those numbers there, you can have a look at them. Remember this half minus a half series and the third series, bring it to 1.5 or 1 upon 1.5. There's some interesting things going on in there. And I think this is where the 1.5 is popping up from a decay series in there. So we'll leave that there for now, and I'll just show you a few things here. I'll show you a few shortcuts that you might like to know. Just a few shortcuts on getting the speed of light for any year. You can use a bit of a shortcut. Now, I showed you the numbers 10 upon 9, 1 upon 2.41, 1.5, and 6, 2, 2, 4, right? Now, this is of course 0.000241, but we're not worried about powers of 10. We're not worried about them at all. Now, I'll show you a couple of things, and I'll show you in green. Okay, here we go. Now, if you divide 1.5 by 6224, now 1.5 billion light years of travel, that's what we reckon, 1.5 billion light years of travel, and at 2006 that was 6224 years of travel. If you just divide that by that, you get 0.0000241. Okay, times a billion. 10 to the 9, there we go. But you get 0.00241. Now you've crushed 1.5 billion light years of travel into only 6224 years, and you've come up with this compression number. And this is Bill Tiff's number here, Bill Tiff's number. I'll write his name up here, Bill Tiff, Bill in the office, William to the will, Bill Tiff. That's his compression number, or the TCN, the Tiff compression number, or if you like, it can be the Tiff quantization number, same thing. I prefer this one, the Tiff compression number. It's 0.00241 at 2006, decreasing. And so that was it. That was the first thing that drove forward the thinking. This finding here. Now, I'll show you a couple other things we found just while I'm going through. We found that 622, I've done this before, cubed equals 0.0000241, but times 10 to the something, whatever it is, 10 to the whatever it is, and 6224 to the power 4 equals 1.5 times 10 to the power something. That's very interesting, isn't it? That it just happened at that date. It's just very interesting. Very interesting, and by the way, now we've found out another couple of things too, just lately, that you remember I said that when you're changing from, if you want to get a half time, and they don't measure the half times, they measure the decay rate, the half time equals 0.693 upon the decay rate. That's how they do it. Decay rate. Down there, upon the decay rate, that's it there. I should have put that line there, should I? Upon the decay rate. So this 0.693, I said you could get by just multiplying this out. And as this number decreases, I think just recently it came to exactly this number here. As this number decreases, this product of this here comes out to exactly here. And we further found that you could reduce this number here, because if you have 10 upon 9, like that, and 1 upon 2.41 times, and 1 upon and 1.5, that's 3 upon 2. That's 3 upon 2, 1.5. So if you look at it, this here becomes 1, and that becomes 3, and this here becomes 5, doesn't it? Okay, so that's 5 upon 3. Now that doesn't look quite right, but remember that we're dealing with slippery powers of 10, and we're going to hold them in disdain. So I'm going to put 0.5 upon 3. Remember, powers of 10, we don't worry about it. 0.5 upon 3. So I'm going to show you that this thing up here is also, different pen, that's also 1/2 times 1/3. 0.5 is a half, times a third, times 1 upon 2.41. That's the number there that represents the change number here. It's not really, they say it's the natural log of 2. But I believe that what's really going on is this here, and that this is decreasing a little bit, and this is where the decrease in radioactivity is happening through this here. And so this here reduces to this down here, and this is concerned with radio decay. And the last thing I'll show you today is this. The last thing I'll show you today is this, that if you want a shortcut to the speed of light, a shortcut to get the speed of light, it might be a shortcut. Some of you might find it easier, but because 1.5 upon 6224 equals 2.41, you see how it's easy to abbreviate things. Also, 1/2 times 1/3 times 2.41, and you can use today's rate, because it's always this, 1.5 upon the elapsed years. So if you want to find the TIF compression number, it's always 1.5 upon the elapsed years. This was 2006, remember? So times that, times, remember that constant I gave you? 4707 times 10 to the 7, k squared. K squared. That equals c squared. So c squared equals a half times a third times 2.1 times k squared. Now that represents speed of light. Now I'm going to give you another one if I can remember it. That gravity is represented by a half times a third times pi squared. And that's gravity. So there may be a connection between gravity, between speed of light, and between radiative decay. Ladies and gentlemen, I'm going to leave it there for today. I hope you find it interesting, and there's a draft paper up on the site with all this on it. So God bless, and I'll see you around. Bye.